Hello everyone. This video is on Knewton Alta assignment section 5.3 part 2 called Zeros of Polynomial Functions. So in this video I'm going to be going over a preview version of this particular assignment. So please understand that the questions I see in this video may not be the same questions that you see when you work on the assignment yourself. But the objectives are the same. So I'm hoping that the questions are similar enough so that watching me do them here helps you out somehow when you do them on your own. Alright, so your assignment page, you have the title, your mastery bar. You can see the objectives. Looks like there are 2 objectives in this particular assignment. Under the current objective, there should be a question related to that objective. And then at the bottom of every question, there should be a feedback button. You can send feedback to Knewton. You will not have this instructor cheat button. So for instructors only. But you will have this more instruction button. Right, if you're struggling with a particular topic, click on this and you'll be taken to a page with some reading or some videos, and then you'll be given questions related to that instruction, and you can complete the assignment going through those questions as well. Alright, so this first objective, use factoring to find zeros of polynomial functions. Alright, so remember, I'll tell you what a zero is real quick. Alright, and then I'll write out this function, and we're asked to, find the zeros of this polynomial function. So let me write out a little definition here first. A zero of a function, say f of x, is any number say x equals r, right, r for root. Okay, sometimes in other texts, I don't know about this one, but other books, sometimes zeros are called roots. So a zero of a function or a root of a function. So that's why I'm using the letter r here. Is any number x equals r, such that f of r equals 0. Basically, a zero of a function is any number that you can plug into the function and get an output of 0. Right? It makes the function equal 0. Okay. So this example they're giving us, right? They have a polynomial function f of x equals x cubed minus 3x squared plus 2x. They're asking us to find the zeros of this function, right? Find the numbers that you can plug in for x here to make f of x equal 0. So the question is, when is f of x going to be equal to 0? So that just means we're solving the following equation. When is x cubed minus 3x squared plus 2x, right? When is this equal to 0? Solve for x, right? And those solutions will be the zeros of this function. And we're going to be solving by factoring, right? The objective says use factoring to find zeros. And I'm assuming you remember how to factor polynomials. So if you look at these three terms here, they all have a common factor of x. So I'll factor x out. And then what will be left over would be x squared minus 3x plus 2. And we still have this product equal to 0. And then this quadratic, this x squared minus 3x plus 2, if that weren't factorable, that'd be fine. You could use the quadratic formula to figure out what makes it equal 0. But it is factorable, right? This factors even further. So we have x still, and then x squared minus 3x plus 2 would factor to x minus 1 times x minus 2. All right, and now I have what I want. I have a product of a bunch of factors equal to 0. And then we can apply the zero product property. Remember what the zero product property states is that, if a product equals 0, then one of the factors has to be 0. So either x equals 0 or x minus 1 equals 0 or x minus 2 equals 0. Right? Just take each factor, set it equal to 0. And then we solve these. Now x equals 0 has a simple solution. It's x equals 0. So there's a 0 of this function. Right? f of 0 would be equal to 0. Right? If I plug 0 in for x, the output would be 0. Next one, next factor, x minus 1 is 0, so x equals 1, right? Add 1 to both sides. There's another one. So f of 1 would also be 0, right? Well, you'd get 1 minus 3 plus 2. That would be 0. And that third factor, right, x minus 2 is 0, x equals 2. Add 2 to both sides, right? And so f of 2, right, is also 0. Right? If I were to plug in 2, I'd get 2 cubed, that's 8. 3 times 4, 2 squared is 12. 8 minus 12 is negative 4, and then 2 times 2 is positive 4. Negative 4 plus positive 4 is 0. So these are the zeros of f. Right? X equals 0, 1, and 2. Those are the zeros of f. They're the numbers that you can plug in to get an output of 0. Okay. So that's all, and that's all they wanted. Right. Now look how they say, they want you to just enter. They already have x equals here, right? They just want you to enter the numbers that are zeros separated by commas, right? So 0 is a 0, 1 is a 0, and 2 is a 0. Right. And that's it. 0, 1, 2. Then after you submit your answer, right, you should be told if you're right or wrong and given an answer explanation, right? Please read through the answer explanations. So make sure you understand why things were correct or incorrect, and hopefully you can learn from your mistakes for future problems. All right, next question. All right, so now we're on the other objective. Identify zeros and their multiplicities from an equation or a graph. All right, so I want to talk more about this word multiplicity before we get into this graph here. All right, so I already defined, what's a zero of a function. Now, something else you may notice, even from this first example here. See how x was a factor of the polynomial, right? This factored to x times x minus 1 times x minus 2. And you could even think of x as x minus 0 if you want, right? X minus 0 is the same as x. And do you see how each of the factors of the polynomial was just x minus one of these zeros? X minus 0, x minus 1, 1 was a 0, x minus 2, 2 was a 0. And that's going to happen for any of the zeros of a function, or of a polynomial function. Right? So I'll say this, big note here, and this is sometimes referred to as the factor theorem, and we may come across this in future sections as well, but I figured why not get it out of the way now. You can probably have already guessed this anyway. X equals r is a zero of a polynomial function f of x, and a polynomial function f of x, if and only if. Now this just means that the implication goes in both directions. So if this, then that, if that, then this, right? So x equals r is a zero of a polynomial function f of x, if and only if, the quantity x minus r is a factor of f of x. And like I said, you probably could have already guessed that based on just that first example. I'll put this in a nice box here. That's important to remember. So like I said, from this first example, you could have guessed that, right? X equals 0 is a 0, and we see x minus 0 was a factor, and vice versa. Right? If you see that x minus 0 is a factor, then you know that 0 is a 0. You see x minus 1 is a factor, so you know 1 is a 0. You see x minus 2 is a factor, so you know that 2 is a 0. Right? Now that word multiplicity came up, and that's another definition I need to get out here. So the number of times x minus r is a factor of the polynomial f of x. So basically the power on x minus r. So the number of times x minus r is a factor of a polynomial is called the multiplicity of the zero x equals r. It's called the multiplicity of the zero x equals r. All right. Okay, so another definition now. Now, there's a relationship between multiplicities of a zero and their graphs. All right, and I'm going to show you that relationship by actually showing you some pictures of graphs. So I'm going to go to the Desmos website. This is a free online graphing calculator, desmos.com. Go to projector mode here, make things a little bigger. And let me show you. All right, so let's say I have f of x equals, and I'll just start off with something with a very simple zero, say x minus 2. So see, x minus 2 is obviously the only factor, meaning that x equals 2 is a 0. See, input 2, output 0. 2 is an x-intercept. Now right now, x minus 2 is a factor one time. Right? It's x minus 2 to the first power. So we'd say it has a multiplicity of 1. Right? And you see how what happens at x equals 2? The graph crosses straight over the x-axis. It crosses over, and I'll draw this stuff out too. Right? So for example, if we have f of x equals x minus 2, all right, this has a 0 of x equals 2, and they would say that the multiplicity of that 0 is 1. Right, because it's x minus 2 to the first power, right? There's only one factor of x minus 2. And then if you were to look at the graph, right, here's 2. There's an x-intercept at 2, 0, and the graph just crosses straight through the x-axis, right? Graph crosses over the x-axis. Let's point that out. Right, well, now let me show you the graph of this function. F of x equals, let's take that factor of x minus 2 and add another factor of x minus 2. Make it x minus 2 times x minus 2 again, or x minus 2 squared. So this would have, since x minus 2 is a factor, it has x equals 2 as a 0, right? But this time we would say that x equals 2 has a multiplicity of 2, because now there are two factors of x minus 2. And we're going to see in a second that the graph of this looks like this. It has, it still has 2, 0, right? 2 is still a 0, but now the graph is going to be this parabola where 2, 0 is the vertex, and you see what's going to happen is the graph will come down, touch the x-axis, but not cross over. It's going to bounce off. Right? So I'll say here, the graph bounces off the x-axis at x equals 2. All right, now I'll show you a better picture on Desmos. All right, so again, just taking x minus 2 here and adding another factor of x minus 2, making it x minus 2 to the second power. And you see that? Right? 2, 0 is still there. Right? It's still a 0 at x equals 2, but the graph comes down, touches, and then bounces off when the multiplicity is 2. All right. Now what happens when the multiplicity is 3? So instead of x minus 2 squared, I'm going to make it to the third power. Now you see how the 2, 0 is still there. Now the graph crosses over again. It crosses the x-axis. But notice it doesn't cross straight through. It crosses a little more flatly. Right, it actually it crosses like a cubic function, like a cubic polynomial would. It doesn't go straight through, but it kind of flattens out. And that's going to happen for the higher multiplicities. The higher the multiplicity is, the flatter the graph gets near that 0, near that x-intercept. And you may have already guessed, when the multiplicity is odd, the graph crosses over the x-axis. When the multiplicity is even, so if I put the fourth power here, you see how it bounces off the x-axis? But again, a little more flatly than it did when the multiplicity was 2. Right, it's a little wider, a little flatter. But it still touches the x-axis and bounces off. It doesn't cross over. All right, and I'll go a couple more here. If I had x minus 2 to the fifth, again, you see it crossing over, but a little even wider and flatter than when it had a multiplicity of 3. All right, so I'll write this out. All right. So what we've noticed, hopefully, from all these is that if the multiplicity is even, right, if you have an even multiplicity, then the graph will bounce off the x-axis. At that 0. If you have an odd multiplicity, As we've been seeing, the graph crosses over the x-axis at that x-intercept. All right, and one more thing to point out, the higher the multiplicity, the flatter, the wider and flatter the graph looks near the x-intercept. So the higher the multiplicity, graph gets, wider and flatter these aren't technical terms, but you saw what was happening, and I'll show you some more. Wider and flatter near the x-intercept, near the 0. So this is huge. This is the big thing to remember here for this objective. All right. And again, back to my page, see there's the multiplicity of 5 for x equals 2. Now if I have a multiplicity of 6, and then look, see 8, 10, you see how the graph bounces off. It's got an even multiplicity, but definitely wider and flatter, near that 0. And then if I go with odd powers, 7, see how it crosses over, but it's pretty wide and flat near the 0. Then 9, wider and flatter. 11, wider and flatter. 13, 15, right? I mean, you see how it basically looks like a horizontal segment almost. It's so wide and flat. But it definitely still crosses over the x-axis with an odd multiplicity. Okay, so that was just a little example there with 1, 0, with one x-intercept. Now let's go back to the actual question. So here we're given the graph of it, and they're telling us it's a degree 4 polynomial. Right? Oh, I guess that's one other thing too. I guess I should have also mentioned that. So another key point is that the sum of all the multiplicities of each 0 I can't spell. Sorry. The sum of the multiplicities of all the zeros is the degree of the polynomial. Now, this is all the complex zeros, not just the real zeros even. All right. So there may be zeros that have an imaginary number in them. Now you're not going to see x-intercepts, right? X-intercepts are for real numbers only, right? The x-axis is real numbers. But still, those zeros with an imaginary number in them also have multiplicities. And the sum of all the multiplicities of every 0 should be the degree of the polynomial, right? So if you take the multiplicity of each 0 and add them up, and you get something higher than the degree, then you know you did something wrong. All right, so back here, right? So when they're saying it's a degree 4 polynomial, the sum of all the multiplicities of the zeros should not be higher than 4. All right. Find all the zeros and their multiplicities. Right. So again, the zeros are where the x-intercepts are, right? What inputs give me an output of 0. So -5, -2, and +4 is where the graph is crossing the x-axis, touching the x-axis. Now, do you see how at -5 it crosses straight through? So it should have an odd multiplicity. And it's not very flat. It crosses straight through. So I'm going to say it has a multiplicity of 1 at x equals -5. Same thing for at x equals -2. See how the graph crosses the x-axis, so it should have an odd multiplicity, 1, 3, 5, 7, but it's not very flat. It's crossing straight through. like a line, right? Like a first degree polynomial. So it also has a multiplicity of 1, I would say. And then over here at 4, you see how the graph touches 4 and then bounces off? Right? It bounces off the x-axis. So this has an even multiplicity, 2, 4, 6, 8. But they said it was a degree 4, so it can't have a multiplicity of 4, because then the sum of the multiplicities would be higher than the degree. And it doesn't look very flat at all. It looks like kind of like just like a little parabola here, like a degree 2. So I would say this has a multiplicity of 2. So negative 5 with a multiplicity of 1, negative 2 has a multiplicity of 1, and 4 has a multiplicity of 2. And then look at which one matches. So it looks like this one here. Right? X equals negative 4 with a multiplicity of 2. Oh, 4. 4 with a multiplicity of 2, sorry. This one here. 4 with a multiplicity of 2, negative 5 with a multiplicity of 1, and negative 2 with a multiplicity of 1. This looks like it matches what I was saying about the graph. And that's it. Alright, then after you submit any answer, it should tell you if you're right or wrong, and then and then give you some answer explanation. Please read through the answer explanations. Actually, I've already said this, didn't I? Well, lost my train of thought already. Yeah, I did say that. Sorry. Alright, so let's move on. Alright, so identify zeros and their multiplicity from an equation or a graph, and here again it is a graph. So it's a degree 5 polynomial. So once again, the sum of all the multiplicities shouldn't be more than 5. Right. So look, you got negative 5 as a 0, and it looks like it has a multiplicity of 1, right? The graph is crossing straight through. Looks like it's touching at 1 here, but bouncing off. And same thing at 4, bouncing off. So I'd say multiplicity of 2 and 2, right? Because they got to be even. And one of these can't be 4, because if you add up all the multiplicities, 1, 2, and 2, that's 5. Right? Remember, the sum of the multiplicities of the zeros should be the degree of the polynomial, and no higher. So negative 5 with a multiplicity of 1, positive 1 with a multiplicity of 2, bouncing off, right? And then positive 4 with a multiplicity of 2 as well. So 4 with a multiplicity of 2, 1 with a multiplicity of 2, negative 5 with a multiplicity of 1. Those are all the things I just said, so it's this first option. Okay. Alright, now we're back to the use factoring to find zeros of polynomial functions. So again, this shouldn't be too terrible. Now notice that here they have separate boxes with commas, so it looks like there's going to be 3 zeros here. Do not enter a 0 more than 1 time, right? So don't enter a 0 with higher multiplicity than 1 more than once. Alright, so I'll write this function out, and we'll factor it and state the zeros. So here we're given f of x equals x to the 6th minus 7 x to the 4th minus 8x squared. And I'm just going to factor it right now. And then we'll look at the factors, and you can state what the zeros are by looking at the factors pretty easily. So these all have a common factor of x squared. So that's x to the 2nd power. Then you have, when you pull out x squared, you got x to the 4th minus 7x squared minus 8. And then this factors, this is like a quadratic, right? This is a polynomial that is quadratic in form. If you want to replace x squared with, say, u, this would be u squared minus 7u minus 8, but I'll leave it as x to the 4th and x squared here. This would be x squared, and then this factors to x squared minus 8 times x squared plus 1. And now, I mean, you can factor this further, just not over the integers. Because this would be x squared minus, the square root of 8 squared. It is a difference of squares. It's just, that's not a nice square. It's not, 8 is not a perfect square, not an integer squared. But I can still think about it like this if I wish and go x squared times, and then this factors to x minus the square root of 8 times x plus the square root of 8, if you want to do that. And then this here is kind of silly, but you can think of this as x squared minus I squared. Remember, I is the square root of negative 1. So you could factor that to x minus I times x plus I, right? But that's going a little too far, I think, with the imaginaries, right? They're only looking for the real zeros, right? They even say in the instructions, find all the real number zeros, no imaginaries. Okay, now say you didn't go that far. Say you stopped here. And they're like, okay, I've factored this as far as I can go. Now let's set it equal to 0 and see what we get. When is x squared times x squared minus 8, times x squared plus 1, when is that equal to 0? Well, when x equals 0, because remember, this is x squared. It's the same factor twice. Or when x squared minus 8 equals 0, then you can use the quadratic formula, or just add 8, take the square root and all that. We're getting x equals positive or negative square root of 8. But the square root of 8, you can simplify to 2 times the square root of 2. All right, this is square root of 4 times the square root of 2. And those are real. Or when x squared plus 1 equals 0. Again, you solve this using the quadratic formula, or subtract 1, take square roots. You get x equals positive or negative square root of negative 1, or positive or negative I. But as I was saying a second ago, right, these are not real, so I'm not counting these. Right. Now, if you wanted to, you could also list the zeros and their multiplicities, and we're going to see that all the multiplicities add up to 6, right? This is a degree 6 polynomial. But here are the zeros and their multiplicities. Well, x equals 0 was a 0, but you see how there are two factors of x minus 0, right? Which is just x. There's x squared, so that has a multiplicity of 2. Positive 2 times the square root of 2, right, is a 0. And the way I wrote it here, x minus that is only a factor once, right? So it's got a multiplicity of 1. And so is negative square root of 8, right? Negative 2 root 2. And x minus that, x plus the square root of 8, is only a factor once. And those take care of the real zeros. And then again, you have imaginary zeros. You have I and negative I. And those also have a multiplicity of 1, right? Because again, when I factored completely over the complex numbers, x minus I was a factor once. X minus negative I, or x plus I, was a factor once. And you see that the sum of all the multiplicities of the complex zeros is 6, which is the degree of the polynomial. Right? And that should happen, right? And we'll see that for every polynomial we come across. But again, they only wanted the real ones. They only wanted the real ones without the imaginary. So 0, positive 2 root 2, and negative 2 root 2, right? Square root of 8. And those are what I'll enter. Right? So x equals 0 works, is a 0. X equals, 2 times the square root of 2, and then negative 2 times the square root of 2. Okay, and again, the real zeros only. Wonderful. And once again, please read through the answer explanations. Okay. Next question. All right, so still using factoring. So once again, I'll write this polynomial out. We'll factor it as far as we can, and state the zeros. So we're given f of x equals x to the fifth plus 3x cubed minus 10x. And I'll just factor it here, and we'll set it to 0 when I'm done factoring. They all have a common factor of x. And I pull out, there's x to the fourth plus 3x squared minus 10. And this is another one of those that's in quadratic form. It's like a quadratic. You could do a substitution for x squared if you want, but I'll leave it that way and say this will factor to x squared plus 5 times x squared minus 2. That would be x to the fourth plus 3x squared minus 10. And again, these can be factored over the complex numbers further. Because if you set them equal to 0, x squared plus 5, when's that equal to 0? Well, that's when x equals positive or negative, I times the square root of 5, or the square root of 5 times I. Right, square root of negative 5, which is imaginary. So if you wanted to, this could factor further. Right? This could factor to x minus I root 5, right, one of the zeros, and then x minus the other 0, which is negative I root 5, so x plus I root 5. And then the same thing goes for x squared minus 2. When is that equal to 0? When x equals positive or negative square root of 2. So this could factor to x minus the square root of 2 times x minus negative square root of 2, or x plus square root of 2, right? I mean, you should be able to factor all these polynomials down to linear factors, degree 1s, but they might have imaginaries in them or square roots in them. Because I know it's a little more than we're used to. Right? We're used to factoring just down to the integers, right? Just factoring over the integers. But once you know the zeros, you can factor further, over the complex numbers. Anyway, I've found them. And then the other factor was x, right? X equals 0 is a 0. And then positive or negative square root of 2. And positive or negative square root of, negative 5 or I root 5. But, these aren't real. These have an imaginary number in them. And again, all they wanted were the real zeros. And every single one of these zeros has a multiplicity of 1. See how each of these factors in the end here, x minus a 0, x minus one of the zeros, is all to the first power. And so all of them have a multiplicity of 1. You add up all the multiplicities of all the complex zeros, you get 5, right, the degree. But just 0 and positive or negative square root of 2 are the real zeros they're looking for, the real roots. So 0, positive square root of 2, negative square root of 2. That should be good. That should be it. Okay. All right, so we're doing this one more time. And, find the real zeros of the following polynomial function. This time they want, basically they want the x-intercepts now. They want them as ordered pairs. It looks like we should be finding 2 of them. Right. So just some x value, comma 0, right? Because these zeros, these roots, are just the x-intercepts of the graph, as you've probably noticed already. Right. So here we're given f of x equals, x to the fourth minus 729 x to the first. I could pull out x from these, and then we have x cubed minus 729. And this x cubed minus 729 is actually a difference of cubes. This is x cubed minus 9 cubed. Remember, I'm hoping you remember how to factor a difference of cubes. That would factor to x minus 9, and then times x squared plus 9x plus 9 squared, or plus 81. Right. And then we figure out what makes each of these factors 0. Right? When is this equal to 0? Well, obviously when x equals 0, when x minus 9 is 0, so when x equals 9, these are going to be the real zeros. The graph is going to have x-intercepts at 0, 0, and 9, 0. And I'll tell you right now, the other one, when x squared plus 9x plus 81, when is that equal to 0? This is going to have imaginary zeros in it, so complex numbers with an imaginary part. I'll do this one by completing the square. We got x squared plus 9x equals negative 81. Half of this would be 9 halves. I'd add 81 fourths. Right? You take 9 halves and square it. So over here, add 81 fourths as well. And this becomes x plus 9 halves squared equals, and if you factor 81 out, it would be negative 1 plus 1 fourth times 81. So negative 3 fourths times 81, negative 243 fourths. Right. Yeah. And then we get x plus 9 halves equals, positive or negative I times the square root of 243, divided by 2. And then we subtract 9 halves here, so x equals, negative 9 halves plus or minus I times the square root of 243 all over 2. And you see these are not real because of the imaginary number there. Right? We ended up taking the square root of a negative. So, I mean, it's degree 4. It has 4 zeros, just 2 of them have an imaginary number in them. 2 of them aren't real. And then, yeah, you could, like I said earlier, right? Once you know zeros, you could factor this further over the complex numbers. This would be x times x minus 9, and then this x squared plus 9x plus 81 could factor to x minus, one of these, negative 9 halves plus I times the square root of 243 all over 2. And then the other factor is x minus the other one, negative 9 halves minus I times the square root of 243 all over 2, right? But that's annoying, right? You see why we don't do that, why we don't keep factoring to the complex numbers too often, because it can be a bit of a pain to write, right? So usually we stop when, we get to the factoring over the integers. All the coefficients are integers. All right, but the only real zeros are 0 and 9. So the x-intercepts are 0, 0, 9, 0. Right, that's what they want. So 0, 0, 9, 0. Okay, so that objective's done with the finding zeros by factoring. And then back to the graphs, or equations, but so far it looks like they've been giving us graphs here. So this one, they say it's a degree 4 polynomial. Find all the zeros in their multiplicities. Now look at x equals 2. See how the graph crosses straight over the x, so it's got to have a multiplicity of 1. And then at x equals negative 1, the graph crosses over, so it's got to have an odd multiplicity, but it's flatter. It's not it's crossing more like a cubic function, not like a linear. So I would say 2 has a multiplicity of 1, and negative 1, that 0, has a multiplicity of 3. And those add up to 4. Right? The multiplicity should add up to the degree. So 2 with a multiplicity of 1 and negative 1 with a multiplicity of 3. Or sorry, yeah, 3 right here. Negative 1 with a multiplicity of 3, 2 with a multiplicity of 1. That's exactly what I said earlier. And that should be good. All right, and one more of these. All right, so again, it's a graph. So negative 5 looks like it has a multiplicity of 1. Negative 1 looks like it also has a multiplicity of 1. Right? It's just straight through, not flattening out. And 1 looks like it has a multiplicity of 2. Right? The graph bounces off the x-axis, so it should have an even multiplicity. So 1, 1, and 2, those add up to 4. So looks like those are probably good then. So negative 5 with a multiplicity of 1, negative 1 with a multiplicity of 1, and 1 with a multiplicity of 2. Let's kind of see which one matches. 1 with a multiplicity of 2. Nope. 1 with a multiplicity of 2. Negative 1 with a multiplicity of 1. Negative 5 with a multiplicity of 1. That's what I said earlier. Great. Alright, and that should be it for this preview version of this assignment. So again, the key takeaways here are, you should be able to know how to factor. Remember how to factor, at least over the integers. Factoring over the real numbers over the complex numbers, we'll get to that eventually, but I was kind of starting you into it here. But you factor factor a polynomial function until you can't factor it anymore, and then set each factor to be 0, and that's how you find zeros. What inputs make the output 0? The x-intercepts, the roots. Right, and then the multiplicities. Right, you just see how many times is x minus that number a factor. That's the multiplicity. And zeros with an odd multiplicity, the graph should cross over the x-axis. Zeros with an even multiplicity, the graph should bounce off the x-axis. And the higher the multiplicity is, the wider and flatter the graph will look near those x-intercepts. And also, for all the zeros, real and non-real, the sum of the multiplicities should be equal to the degree of the polynomial. So that's a lot of stuff, I know, but if you keep that stuff in mind, this assignment shouldn't be too much of a problem. All right, and as I said at the top of the video, please understand that the questions I saw here are not exactly going to be the questions that you see when you work on the assignment yourself, but the objectives are the same, right? So I'm hoping that watching me go through these here help you in some way when you work on the assignment on your own. And thank you very much for watching.